Okay, so I think there were a lot of questions during the break, like many of them could be clarified as we progress. Okay, so if we still have more questions, I will take it again. Okay, so before the break, we looked at the idea of margin, right? Like, and we said, okay, we're gonna rescale things in such a way that the margin, which is the closest distance, right, is always one. So that every other data point is going to be at distance greater than one, right? And we start with this final observation that when a max margin algorithm converges, it's going to find a line which will have at least two closest data points, right? One of them will be circle, one of them will be cross. And these circle and cross, the distance for them is going to be exactly one. Is that clear? Okay, so this is where we stop. Now we can go back to the objective function we had, right? So maybe I'll take this objective function to the first slide. Okay. Now with the new formulation, we know the answer for this minimization problem. It's always going to be one, right? So we did reparameterization in such a way that the margin is always one. So I don't need to do this inner loop. So the new formulation is given by R max W, B 1 over W. That's it. However, subject to the constraint, the subject to the constraint that T of n times W transpose P of xn plus B is greater than or equal to 1 for n is equal to 1 to n. Okay. This looks, at least the objective looks easier than the previous objective, because the previous objective had an R max followed by a minimization argument inside, right? So here, instead, you're maximizing 1 over W. However, this is not an unconstrained problem anymore, but here's a constraint, which is subject to P of the times the transpose xn plus B is greater than or equal to 1. Is it clear? So we're going to solve this constraint optimization problem, which is hopefully easier to solve than the previous formulation. Okay. Now, we always like to minimize things. So I'm going to convert this into R min WB. Okay. Instead of 1 over W, we go to W. Just 1 second. So I'm also going to do 1 over 2 W squared. Okay. This is not going to change the solution, right? Instead of R maxing 1 over W, I'm doing 1 over like 1 by 2 W squared, 1 by 2, we know by now why we add this 1 by 2, right? And so, and squaring is not changing the solution either. So subject to the constraint that T of n times W transpose P of xn plus B is greater than or equal to 1 for n is equal to 1. Okay. Now, this minimization problem that you see here, right, is called quadratic programming problem in optimization literature. It's quadratic programming because you have a quadratic objective subject to linear constraints. Okay, if you have linear objective subject to linear constraints, it's a linear programming problem. Okay,
Why don't you divide by two? So I get this.
it's a little easier to differentiate. Okay, so whenever you differentiate that, that's the classified. Okay, so if you have a linear objective followed by linear, like linear constraints is a linear programming problem. In this case, this is called quadratic programming because you have a quadratic objective with linear constraints. Is that clear? So, so we know how to solve unconstrained optimization problems using the gradient descent. Right? If you want to do, if you want to simply do or min of something, you will do gradient descent. But if I ask you to do or min of something subject to certain constraints, we haven't seen algorithms to do this in the class. Okay. But if you take an optimization course, and if you take a balance optimization course, or linear optimization or non-linear optimization courses, that you will see different algorithms like for solving constraint optimization. And I think for the purpose of this course, like you don't need to get into the details of how to solve the given problem. But all you should know is there are various standard packages that exist, like where you could just define a given problem. It's going to solve the problem for you until you what are the parameters. Is that clear? Any question? Yeah.
I'm not sure to understand the game. I understand the one thing is the you put one at one and then the others at greater one. But we still have to look for all of the points to verify that their distance is all greater than one.
Yes.
So we still have the same number of calculation.
Yes, it's just that we have a max min optimization. Solving that is harder, but there are efficient solvers available for keeping problems. Okay. There was another question. Like, did you have a question?
No.
Okay. Okay. So now this is one way to solve this problem. Okay. We're going to look at for any constraint optimization, you could actually write it as an unconstrained optimization problem, which is basically the Lagrangian formulation of the problem. Okay. So if you remember our discussion on L1, L2 regularization, right? So we wrote two versions of how to do regularization. Like so one, which was unconstrained, is basically plus some coefficient time L2 regularization, right? The other version was having some constraint, right? So similarly, like we can do the same thing here. Like so, we can write the Lagrangian formulation of this constraint optimization problem. Okay, so the Lagrangian formulation is given by 1 over 2 w squared. Okay, like I want to convert this into an unconstrained problem, which means I'm going to do this plus some a times this. Okay, but the constraint is maximizing. I want to switch it into minimizing. Right, so I'm going to put a minus. So minus summation n is equal to 1 to capital N a n times T n W transpose P of x n plus P minus 1. Okay, so what I did here is I took this constraint T n times W transpose P x plus P greater than or equal to 1. I put the 1 to the left. So this becomes Tn plus y of xn minus 1 greater than 0, right? Which is maximizing. I'm switching it into minimizing and putting minus to the left, right? So then this becomes this minus summation n is equal to n a n times this. So a n is basically the strength of the second term. Okay, so here where a, which is a1 to an, equal to 0. So this is basically the Lagrange modifier. Okay. So now we can solve this problem, right? You can actually differentiate this with respect to W, with respect to B, with respect to A, right? So let's try to do that. So first we will do dou L by dou W. I'm differentiating with respect to W. So which terms are affected? First term is affected. In the second term, just the part which has W is affected, right? So when I differentiate the first term, I'm going to get simply W, okay, minus summation n equal to 1 to capital N, A N T N P of x. So this is equal to 0. I'm differentiating and setting it to 0 so that I can find in this case value. Okay, so from this, I can write W as summation n is equal to 1 to capital N, A N T N P of x. Is that clear? Okay, so given that we are very close to the midterm, like I want you to take a few minutes and do this dou L by dou B yourself. So, really practice. So, can you differentiate this term with respect to B and set it to 0 and find the solution? It is very easy. Right? So, most of these terms will become 0. Okay, I'll give you 2 minutes. So when you're differentiating with respect to B, the first term is 0, right? The second term actually has 3 terms inside, I guess. Yeah, it has 3 terms actually, and 2 of them is going to be 0. So what is left? So minus, there's a minus, right? So minus summation n is equal to 1 to capital N, A and T N is equal to 0. Which means when a different, I'm not getting the value of B now, okay? So it's this is just saying that, okay, summation n is equal to 1 to capital N, A and T N is equal to 0. This is what I get. Yeah?
Where the T-N?
Because there's a T N that is outside the bracket.
Outside.
Yes.
Outside the bracket.
Oh,
I didn't.
okay, maybe I should have added a,
One. Yeah.
okay, maybe I should have added another bracket. No, no, I have correct brackets, no?
After the.
Oh, yeah,
after
okay.
the-
Yeah, I should have added this extra bracket. Yeah.
You missed one on the other spot.
Yeah, after the P of xn, you have one in the total.
Where?
After the xn, like there's
There's an excess bracket.
yeah. Is that-
Well, this bracket is this.
just before the plus b. If you
Okay, but you know what the problem is? I'm not gonna try to fix it here, the whole W transpose P of xn plus B is multiplied with G of x. Okay, yeah.
before with the linear models, we were sure that that we would find a solution because it was convex.
Yes.
How on this are we sure that we'll find the minimum for the
Okay, let's talk about the convergence in the end. Okay, so for now, let's try to solve the problem. So we'll talk about the convergence in the end. Okay, so now we also need to do. Okay, I can actually use these two information and try to update my objective. Okay, I can write. Okay, first I'm going to write the current objective, which is L of WBA is equal to 1 over 2 W square minus summation n is equal to 1 to capital M A N times T N. Okay, let me try to write this correctly now. So W transpose P of X N plus B over bracket minus 1. Okay. So now I found values for W and B, right? So I can write the modified Lagrangian objective with just A as, so the value of W is this complex thing, right? So when you do W square, this is going to become double summation. So 1 over 2 summation M is equal to 1 to capital M, summation M is equal to 1 to capital M, A M, A M, T M, T M, P of X n transpose P of X M. It looks very complex, but all I have done is took this W and then W squared. Okay. So that is this term. So then we have minus summation n is equal to 1 to capital N, A n times. Okay. Okay. Again, you have a W here. So which means you need to put another summation. So I'm gonna write this directly. You can look at it. You get it converted. So M is equal to 1 to capital N, A M, T M, T M, P of X n transpose P of X M. So the plus B, right? Like, so it becomes minus summation n is equal to 1 to n, A n, T n times B. But we know from the previous slide that that summation is 0. So that whole term becomes 0. So then the only thing that is left is just the minus 1. So minus 1, then you want to play with minus summation A, it becomes plus summation n is equal to 1 to capital N A. Okay. So this is half times some value minus 1 times the same value. So I can write this as simply, I want to find maximize A summation n is equal to 1 to capital N, A n minus 1 by 2 summation n is equal to 1 to capital N, summation m is equal to 1 to capital N, A n, A m, T n, T m. Okay. So then you have this P transpose X, Px transpose Px, right? So that I'm going to give a name for it. So we're going to write KXN XM such that AN is greater than or equal to 0. So this is the condition from the Lagrangian problem. And also we have another constraint, which is summation n is equal to 1 to capital N, A n T n is equal to 0. Okay. So this is, so now we have arrived at another constraint optimization problem where I'm going to define kx dash as simply p of x transpose p of x dash. Okay, this has a name, it's called a kernel function. Okay. Now, the exact way in which I arrived here, if you missed some steps, that's okay. You can go back and like revisit this. But what is important is when I switch from the original formulation to the Lagrangian formulation, I was hoping that I could just differentiate it, set it to 0 and find some solution, right? However, I arrived at another constraint optimization problem. Okay, this is also QP, right? So it has quadratic objective with linear constraints. This is also QP. So I can use the same QP solvers to solve this problem as well. Okay. Now, why should we do all these things if we arrive at like another problem, which is also quadratic programming problem? We're going to talk about that question.
Why the phi of x is transpose?
Well, that's what the equation here is. This is just to make sure that things match. Okay, so the two formulations that we have, right? The original formulation and the new formulation that we arrived at from the Lagrangian like method, right? So they actually have a name in convex optimization literature. Okay, so the first problem, the original problem is often referred to as primal problem. Okay, so the primal problem for max margin classification is R min WB 1 over 2 W squared, subject to the constraint that Tn times W transpose P of X m. Okay, this is always hard for me to write. So plus B is greater than or equal to 1 for n is equal to 1. Right? So this was my primal problem. Right? So the dual problem that we derive now is max A, which is summation n is equal to 1 to capital N minus 1 over 2 summation n is equal to 1 to capital N, m is equal to 1 to capital M, A n T, sorry, Tn Tm K of xn xm such that an is greater than or equal to 0 for n is equal to 1 to n, and summation n is equal to 1 to capital N, an Tn is equal to 0. Right? Okay. First, let's talk about what can we do as the solution to these problems. Like let's start with the primal problem. If you take the primal problem and use cube solver to solve the problem, so what would you get? What do you get out of the primal problem? Like what would you get if you solve the primal problem? So what would you get when you solve the primal problem? Anyone? Yeah. You'll get W and B, right? Like so when you solve the primal problem, you're going to get W and B. So once you have W and B, you know how to do classification. All you have to do is compute Y of xn, which is W transpose P of xn plus B. And if it is greater than 0, it's class 1. If it is less than 0, it's class 2, whatever. Right? So we know how to use the solution of the primal problem. Now let's talk about the dual problem. If I solve this dual problem, so what do I get out of it? A. So we get A. So how can you use A to make predictions?
Can we return to the primal problem with the value of A we just got?
So with the value of A you got, you might need to go back and try to find W, right? Well, then it kind of beats the purpose of having done all this hard work to arrive at the dual problem, right? Like so the dual problem actually has some interesting implications. Okay, so we're going to see how to make use of the solution of the dual problem. So okay, so first let's do that. Then we will discuss the benefits of primal versus dual. Okay, so the question is how to use the dual solution. Okay, so the dual solution is not giving you W and B. Right? So we know that W is basically summation n is equal to 1 to capital N A N T L times P of xn. Right? So this is what we derived previously, right? So which means I can write my y of x as simply W transpose P of x plus B, which is summation n is equal to 1 to capital N A N T N phi of xn transpose phi of x plus b. Okay, so this is, we're going to call this classifier as our dual classifier. So the interesting thing about this dual classifier is there is no W. I got rid of W by using this equation where W is summation k and p of xn. Is that clear? So there is still B. We need to find B, but there is no W in the dual classifier. Once you get the solution for A, if you can find B, then you can directly use this equation. Yeah.
What does A represent again?
A is the Lagrange multiplier. So it's basically like the term you added, like when you convert to the form, right? So now there's no W. This is different from the initial. We will call the initial classifier as the primal classifier. Okay. So the primal classifier had W and B. The dual classifier has no W. There's another interesting thing happening here, which is whenever I want to make a classification prediction for a new x, I'm actually doing summation over n is equal to 1 to n, and I'm doing a dot product of p of xn with the given x. Right? In some sense, you can consider this as some sort of similarity function. So you're trying to do the dot product of the current input and all the training examples, and you're trying to make sense out of like what could be the corresponding y for this example. So this looks very close to a classifier we have seen before. What classifier? So which classifier looks at every example and trying to make a prediction? Yeah. KNN, right? It looks almost like a KNN in the sense it's doing something else for sure, but it looks like KNN in the sense KNN, given a new example, will go check all the examples and find the closest one. This time, right? You can also use similarity functions for KNN, right? Find the most similar examples, do an average, right? We're doing something similar to that here. Okay. So the dual classifier actually looks at all the examples and is doing the dot product between phi of xn and phi of x. Is that clear? So just from the look of it, it looks like a very computationally expensive classifier, right? If you have a million data points, then the dual is actually going through all the million data points, it's computing this dot product, and using that to make a prediction. But basically taking the average of the closest peers. Right? So it still looks like this is not a good idea because like it's a lot of work. However, I want to show you that this dual classifier is doing something much smarter than k-nearest neighbor, and it is actually much cheaper to compute. Okay, so to do that, we need a little bit of optimization background. Okay, so whenever you have a dual problem, they have to satisfy a certain set of conditions. These are called KKT conditions. Okay, so then after the three scientists who discovered these conditions, I think one of the like or two together, one separately, I'm not sure. So what are these KKT conditions? So the KKT conditions say that whenever you have this kind of constraint optimization, right? So the Lagrange multiplier should be always greater than or equal to 0. That is the first condition. Okay. The second condition is basically the constraint, which is T of n times y of xn minus 1 should be always greater than or equal to 0. Right? So the first one is coming from the definition of Lagrange multiplier, the second one is coming from the constraint that we have the problem. Right? The third one is non-trivial. So the KKT condition says that the product of these two conditions should be always 0. So which is an times Tn y of xn minus 1 should be 0. Okay, so why is this true? We will not get into the theory. I highly encourage you to go read about state optimization, like as a background or do an optimization code. Okay, but let's just accept that these three statements are true. Because then the rest of the discussion is easy. So if these three statements are true, okay, so what does this mean? This means that for every, okay, so just observe this carefully. So for every data point, okay, either an is equal to 0 or tn times y of xn is equal to 1. This is an important observation, okay? So this do you agree? So if this statement has to be true, either this has to be 0 for data point. If this is not 0, then this has to be exactly 1. So what does this mean? This means for every data point, either the an is 0 or the data point is in the margin. That is the closest data point. Right? This is the definition of margin, right? So when this is equal to 1, this is the definition of margin. So this is a nice result because now I can actually go back to this expensive classifier and throw away most of the data points in the summation. So all I have to keep in the summation are the data points in the margin. Because for data points that are not in the margin, any condition says that a is 0. The whole term is 0. Right? Is it clear? So when we go back, I'm going to rewrite the equation. So y of x is equal to w transpose phi of x plus b, which is summation n is equal to 1 to capital N a n t n phi of x n transpose phi of x n. Sorry, there is no x n, just x plus b, right? So this summation, I can actually get rid of most of the terms. If you have a million data points, you can get rid of almost all of them except for the data points in the margin. Okay, so this can be written as summation m belonging to the special set of data points that exactly lies in the margin. We're going to call these as support vectors. an tn phi of xn transpose phi of xn plus b. Is that clear? So if I have a problem like this, and I have a, then the only points for which an is not 0 are these 4 points. Okay, so which means I only need to keep these 4 points. We're going to call these 4 points as support vectors. Okay. Now these support vectors are typically much smaller in number than the number of examples you have. Okay. So unlike k-nearest neighbor, which has to store all the examples and compute the similarity with all the examples to come up with the prediction, this algorithm, the dual classifier, can get rid of all the, like you could have hundreds of examples. Like you could have many more examples here. Okay. So you could just get rid of all the examples and just keep these 4 examples. And every time somebody gives you a new x, all you have to do is the dot product of these 4 examples, like with the parent x, and take an average of their predictions depending on similarity. Is it clear? So this is the power of the dual formulation. So the primal is nice, but the dual has a different purpose in the sense like it stores a very small set of examples and computes the prediction based on this small set of examples. Is that clear? we still haven't figured out how to do the how to come up with B, right? Like, so that part still exists. Yeah. Question.
Before you said that for KNN, the definition of a neighbor is a hyperparameter.
Yes.
Is this like?
That's a good point. So we'll talk about this. So for KNN, definition of neighbor is hyperparameter, right? I can actually play with this definition here as well. Okay, we're going to talk about this like in a few minutes. But for now, is this idea clear? So this max margin classifier, because of this reason that the duals population has these support vectors, right? Like so, like is called support vector machine, the whole algorithm. It is one of the most popular machine learning algorithms, like which dominated the field in 90s. Okay, so when neural networks were down, like for a decade, like so the whole field was dominated by support vector machines. Okay, partly because they have very strong theory and they are in principle sound learning algorithms. We will not talk about the convergence in detail, but these algorithms come with convergence guarantees, efficient solvers that you can actually like easily apply them for different tasks. Is it clear? So another important anecdote here is, yes, this is a very rigorous, theoretically sound algorithm, but that's not the only reason why they were popular in 90s. Okay, so one of the main reasons why support vector machines was like popular over all the other machine learning algorithms in 90s is because of this package called libsvm. Okay, libsvm. Well, I don't think it would be Python. Or I don't know, was maybe it wasn't. I don't know. Anyways, this is not Python. So libsvm is actually a C package, and it was an executable. So they were not even releasing the source code. libsvm was like a well-structured executable file that someone who doesn't know how to do programming can just download libsvm.exe, show them where the data is. It's going to give you the classifier. Okay, it was so accessible that people were using SVMs in all the fields that you can think of: physics, chemistry, biology. Like so, any prediction problem that people had, it was very easy for them to do SVM, which is one of the reasons why it was popular. Okay, so this shows the power of, well, not just coming up with a good algorithm, but also a good package that people can use. Like so, you can come up with new algorithms, but if it is very difficult for somebody to implement and use, nobody will use it. So at this point, there are 10,000, 20,000 papers published in machine learning every year. Okay, I'm pretty sure there are many, many really interesting algorithms being developed every year, but most of them never get used because people don't make it accessible enough that somebody can just download, run it, right? Like so, I think this is a very interesting historical anecdote about SVMs. Like so, it shows the power of having a good accessible code that anybody can use it, even someone who doesn't have a good programming background, right? Okay, so I will come to this question of, I don't know who asked, but like, I'll come to the question of like whether there's notion of different similarity functions or distance functions like we had in K-means neighbor here, right? Because that's an important question. But before we go there, let's finish this algorithm, right? So we have everything except B. So we need to find B so that we can actually use this algorithm. Right? So how to get B? Let's do that, then we'll go talk about the similarity function. So how to get B? Okay, so this is actually really simple. So we know that for support vectors, Tn times the prediction is going to be 1, right? So for support vectors, like let's take any support vectors. For support vector, let's say xn, we know that Tn times summation m belonging to S, which is a support vector, am tm kxm xn plus b is equal to 1. right? You can actually solve this equation for p. You will get a value of p. I'm not going to do that here, but like at this point it's easy, right? So you solve this equation, you're going to get the value of p. Is that clear? Okay, so now let's go back to the question which was about the similarity function, right? Like, so how is this similar to what KNN is doing? So I'm going to rewrite the dual classifier. The dual classifier is given by y of x is equal to m belonging to the support vector set an tm phi of xm transpose phi of x plus b, right? We defined this term as a kernel, right? Like, so this, I can write this as summation m belonging to the support set an tm k of phi of x m phi of x n plus b, where k of x x dash is given by x transpose x dash. This is the kernel function. Okay. Now this is where you can try different things. Okay? So for example, there is no reason you should compute similarity as x transpose x dash. You could come up with your own ways to define the similarity. Okay, this could be a hyperparameter. Okay, now you can change this and you're going to get different kernels. So this is like the basis functions, like how we had polynomial basis functions, Gaussian basis functions, right? So we have different types of basis functions for coming up with nonlinear features, right? So similarly, you can come up with different kernel functions, and the simplest is x transpose x, which gives you a linear support vector mission, right? You can actually construct nonlinear support vector missions by just changing this kernel function into some nonlinear function. Is that clear? Okay, so let me show you some examples. Like for example, I'm going to define my kernel as x transpose z the whole square. Okay, I'm taking x and z instead of just doing x transpose z, I'm doing x transpose z squared. So now let's assume that x is two dimensions, x1, x2, and also z is two dimensions, z1, z2. Okay, then the kernel of xz can be written as x transpose z squared, which is x1 z1 plus x2 z2 squared, right? This can be written as x1 z1 squared plus 2 times x1 x2 z1 z2 plus x2 squared z2 squared, right? I can rewrite this as x1 squared square root of 2 x1 x2 x2 squared times z1 square root of 2 z1 z2 z2 squared. This is basically, this can be represented like this. Okay, so this is the beauty of kernels, right? So I am actually directly using x and z, but it is equivalent to using these features. Okay, now you see the features are nonlinear, right? So if you use this squared kernel, then you get these nonlinear features. Now, these are implicit features in the sense you are never explicitly computing these features. You are just feeding x and z to the SVM. It is internally using these nonlinear features to make the computation.
So what does the kernel function do again between the 2 points? Like what does it evaluate? The similarity between?
Yes.
Okay.
Okay. So this idea, right, of using a linear SVM, but with a different kernel, which makes it a nonlinear SVM, right? So this is called kernel trick. Okay. So you could actually take linear models and you take any linear models and find the dual version and do the kernel trick and make it nonlinear. Is it clear? So now we have learned a second way to make linear models nonlinear. Okay, so previously in the class we learned about how to make linear models nonlinear. Like what did we do? So we took a linear model, and instead of passing x, we were passing phi of x, right? So where the phi of x are nonlinear basis functions, right? So this is one way to make models nonlinear. Like so, you take a linear model, you feed in nonlinear features, they're going to get nonlinear predictions, right? Now the second way to make models nonlinear, like make a linear model nonlinear, is what we learned today, which is to take a linear model, okay, but I'm going to convert this into something with nonlinear kernel. And I'm just feeding in S and making predictions, right? But this model is also nonlinear. Is that clear? Now, you can actually do certain things with the kernel trick which you cannot do with basis functions. Okay. For example, if you use a Gaussian kernel, okay, so Gaussian kernel is defined as x of minus x dash square by 2 sigma square, where sigma is a hyperparameter. Okay. What would be the corresponding nonlinear features of this Gaussian kernel? Okay, so I can try to derive it. So x minus x dash square can be written as x transpose x dash, sorry, x transpose x plus x dash transpose x dash minus 2 x transpose x dash, right? So when I do kernel of x dash, it's actually x of minus x transpose x by 2 sigma square times x of x transpose x dash, sorry, x dash transpose x dash by 2 sigma squared times x of x transpose x dash by 2 sigma squared. Well, in the two might get cancelled. Is it right? There's a minus, there's a okay, I think this may be minus. Okay, I might have made some mistakes here, but I'm essentially applying this to F1. Okay, so how do you separate this into x and x dash features? So it turns out that this is not that easy to separate. This is actually equivalent to having an infinite dimensional feature. Okay, so this is equal to using an infinite dimensional basis functions. So which you cannot do in practice. And in practice, if you're using basis functions, you cannot come up with an infinite dimensional basis. However, if you're using kernel, Gaussian kernel, it is implicitly using an infinite dimensional basis functions internally. So it's much more powerful. Yeah.
I don't get it. What is it that we found hard about this form?
Well, you're trying to separate out things which are in exponential sense. So when you try to write it like as just a vector of x, vector of x,
We can't separate
yes.
this. Okay.
Is it clear? Well, I know I'm taking a bit more time, but let me finish this, like so that we see new thing after the break. Okay, so it's just a few more minutes. So is this idea clear? Okay, so now I want to go back to, well, maybe we can stop here. Okay, maybe we can stop here. So what we have done so far is like, so we started with the primal formulation, we converted it into the dual, and then we learned that in dual, instead of having a summation over everything, you can throw away most of the things and just keep the support vector, right? So that makes dual classification more attractive because it's actually much more interpretable as well, right? So it tells you, oh, these are the support vectors. I'm going to say that this class, this example is this class because it has this similarity with the support vectors, right? And we also talked about how the similarity is defined using the kernel trick, and we discussed how you can actually come up with non-linear SVMs by coming up with different types of kernels. I know you did sklearn yesterday, so they might not have covered SVMs because I haven't taught it. But if you go back and check the documentation of sklearn, you will see an SVM classifier where you can set a hyperparameter and say, oh, I want to use this kernel, I want to use a linear kernel, I want to use a Gaussian kernel, I want to use some other kernel, right? Like, so you could set the kernel as a hyperparameter in SVM. Is that clear? Okay, so we can stop here and take a break.